Okay. Can everybody hear me? Yes? So good evening. I'll let everyone take their seats. Welcome to the UQ Energy Express seminar. My name is Peter Ashworth. I'm a professor here in the School of Chemical Engineering, and I hold a chair position in Sustainable Energy Futures. I first of all would like to acknowledge the traditional owners of the land where we gather and meet and pay my respects to elders past and present. I look after the Master of Sustainable Energy, and it's a great privilege to have someone like Emeritus Professor Steffen here to present. Through the program, we have a series of 8 intensive weeks, and when we were looking to do climate science and policy through a review a couple of years ago, it was trying to work out who would be a great person that could come and talk to the students on climate science. And I think I first met Will back in, early 2000s probably. I was at CSIRO and trying to understand what was going on in the climate science government policy arena. And I think we've sort of remained friends and colleagues ever since. So Will has been very generous in sort of working into our program, and the feedback that comes from students is always really positive, and I think we're very privileged to have him here tonight. So just to be aware that Will started this morning lecturing at 9 o'clock. In the middle of the day he went up and was videoed for our MOOC, and now he's back. So he really hasn't drawn breath, and I think that sort of shows the enthusiasm. You can see up here this huge list of accolades about Will. I'll just read a little bit more about his biography, but most of you would have seen that. And then the format for tonight is Will's going to talk for about 40-45 minutes, and then I've invited 2 panellists, and I guess I've sort of tried to reach into the sort of youth of the university, so much younger than myself. So we're going to hear from Belinda Wade, and I'll tell you a little bit about her later, but she's a lecturer in the business school. And then one of our Masters of Sustainable Energy students has agreed to participate too. We had to twist his arm a little bit, but it's fantastic. So what can I say about Will? He's an Earth System scientist, a counsellor on the Climate Council of Australia, Emeritus Professor at ANU, a Senior Fellow at the Stockholm Resilience Centre, and a Fellow of the Bayer Institute of Ecological Economics in Stockholm. He also works with the Canberra Urban and Regional Futures Program and is a member of the ACT Climate Change Council, Chair of the jury for the Volvo Environment Prize, and a member of the International Advisory Board for the Centre of Collective Action Research in Sweden, and a member of the Anthropocene Working Group of the Subcommittee on the Quaternary Stratigraphy. That's a mouthful. So his research interests span a broad range within the fields of climate and Earth system science, with an emphasis on incorporation of human process in Earth system modelling and analysis, and on sustainability and climate change. And I think, for all of us and the students that I'm working with, there is no greater challenge, I don't think, when we think about the problem of climate change and how we transition. And I know that, Will's done a lot of work in this area, so I think we're very privileged to hear him tonight. So Will, I might ask you to come up and share your thoughts on the Anthropocene. Where on earth are we going? So we'll just... We've just got to change the mics.
Okay, thanks very much for that very kind introduction. And what I'm going to try to do tonight is to take you through a quick tour of this new idea, this new concept called the Anthropocene. That's now been around for about 15 years or so. Quite controversial, quite interesting, and quite challenging. So I'm going to start then by, let's see if we can get this going. It's not clicking. Have I got it right? I can do it manually from down here. There we go. We got it going. Great. Thank you. Right. So I'm going to start then. There we go. By a very simple but important concept, and that's the Earth system. And notice that I use singular, system, not systems. We're used to talking about the climate system and the economic system and the hydrological system and all this sort of stuff. And classical Western science loves to break it down into smaller and smaller units and study them more and more. But the whole concept of what's happening to the planet requires us to understand the Earth as a single very complex system. And there's a lot of really good evidence for that. We only need to go down to the Australian Antarctic Territory and look at some of the cores that have been brought up from the ice there, and look at what they're telling us. This graph I'm showing you here is a proxy for temperature, for global average temperature, and it actually goes back 400,000 years. That K there is thousands, so it's 400,000 years, and you can see a very rhythmic pattern of warm periods, ice ages, warm periods, ice ages, and so on, about every 100,000 years. It's really important for us because it encompasses all the time that fully modern humans have been on the planet. So we evolved about 250,000 years ago. We've been through 2 cycles of ice ages, warm periods. So this is our planetary home. This is the Earth that we know. This is the Earth that our physiology and our bodies are adapted to. If we look at the last 100,000 years in more detail, we'll see how important this last bit is. It's important because it was only in this last 12,000 years we've been anything other than hunter-gatherers. So if we look at that blown up last 100,000 years, you can see how erratic an ice age actually is. Very uneven climate, very cold, dry. And then we had a very rapid transition out of that, starting about 20,000 years ago. And about 12,000 years ago, climate steadied out. The geologists have a name for this last fairly steady 12,000 years. It's called the Holocene. The time before it is called the Pleistocene. But the really important thing is that this is the only period during our time on Earth we've been able to develop agriculture and develop settlements, cities, more complex economies, more complex technologies, and the increasingly globalized society that we have today. So it really is a planetary sweet spot, if you like, for humanity. But the interesting thing is this is changing very fast. And as part of an international program I was part of back around 2000 and so on, we decided we needed to look at how the Earth system as a whole was changing. We had a pretty good suspicion that humans were really important in how the Earth was changing. So we decided we needed to systematize all the fragmentary data that was coming in. So we said, all right, how can we characterize what we call a human enterprise in 12 graphs, 12 indicators? This is what we came up with. The usual things: population, economy, energy, urbanization. And then we had some resource use and some communication and transport. And we wanted to go back before the Industrial Revolution because we thought that obviously was a pretty important point in human development. So each of these little graphs go back from 1750 to 2010. We published this in 2015. So 2010 was the last period where we had really comprehensive data. Obviously, you see enormous increases in all of these parameters. But what struck us as really interesting was we expected more of a linear change from the beginning of the Industrial Revolution to 2010. We didn't see that at all. We saw not much action in the first part of this period. And then around 1950, which is where this vertical broken line is, things absolutely took off. An enormous increase in human numbers, economy, activity, resource use, and so on. And it got the nickname very quickly by social scientists of the Great Acceleration of human activity. Now, a lot of people on the human side of things, particularly in the economic side, would say this is progress. This really shows how we can feed, clothe, have really good ways of life for many of the 7.5, 7.4 billion people that are now on the planet. But we Earth system scientists said, wait a minute, you've seen one side of the equation. We've got a lot of data that says things are changing at the level of the entire Earth system. So our challenge was to make a companion set of 12 graphs that actually characterize the Earth system as a whole. And that's what we do here. Exactly the same time scale, 1750 to 2010. The top 6 are what we call the geosphere, the non-living part of planet Earth, the atmosphere, the oceans, the climate. So here you have the famous greenhouse gases, CO2, nitrous oxide, methane, the stratosphere, the ocean, acidity, and this one's climate, surface temperature. The bottom 6 are equally important because they're the biosphere, the living part of planet Earth. And of course, to understand the Earth system, you need to understand both the geosphere and the biosphere, and really importantly, the interaction, because they're tightly intertwined together. So we have the ocean, we have the coastal zone, and we have land. And we chose a number of indicators. You can read what they are. But the interesting thing is, again, we see all of these sweeping up. And again, in many of them, we see changes in rates around the middle of the 20th century. It isn't as consistent as for the human side because there are buffers and lags and so on built into the Earth system. But it's remarkable about just how many of these do change quite remarkably around 1950 or afterwards. So we analyzed a lot of the scientific papers, the data, and so on that went into these. And there are two things we can say for certain about the Earth system based on these graphs. One, it is no longer in the Holocene. All of these parameters are outside of the Holocene envelope of variability, without a doubt. And the second thing we can say, which is really important, is that this is not natural variability. In each case, we can say that the primary driver of the changes that we're showing here with these indicators is driven by human activity. So now we can put the pieces together that we have this remarkable creature, Homo sapiens, that has become incredibly powerful, incredibly active, very technologically advanced, but at the same time is significantly and extremely rapidly changing its home planet. This is a completely new situation, of course, in human history and really in Earth history. To give you a visual idea of how big this change really is, National Geographic decided they wanted to do something on the Great Acceleration. And so they said, you got 12 indicators, that's too complicated, we've got to simplify it so our readers can understand it. Let's use 3, and they used a fairly well-known IPAT equation. That the impact of human activity is some combination or aggregation of population times affluence, which captures consumption, times technology. So that's the IPAT identity, which actually goes back to 1974. Paul Ehrlich and John Holdren developed that. So they visualized it. There's population, here is technology, and there is consumption. And inside this box is stuff we consume. You see there's an airplane, I think there's some fridges, cars, all sorts of stuff in there. And they wanted to use 1900, which is this tiny little box down here, and 2011, which is the big one. And so they contacted me to be a consultant on this, and they thought I'd be really pleased with this, having been the lead author on the Great Acceleration graphs. And I wrote back to them really cranky. And I said, you've absolutely missed the point. I said, what do you mean? I said, you haven't put in 1950. And they argued with me, assuming that 1950 would be halfway up. And I said, put in 1950 and you'll see what I'm talking about. There is 1950. So there's 1900, 1950, and the next half century is the explosion, the Great Acceleration. They were actually astounded when they saw it. And I said, this is great because you're showing visually what we geeky scientists are showing in graphs, the explosion of the human enterprise after the Second World War. So this is really a really great visualization of the Great Acceleration. Well, when all this data were being put together as part of an international research program I was involved with, a gentleman named Paul Crutzen, very well-known scientist, atmospheric chemist, he's a Nobel laureate for his work on the ozone hole. He was one of the 3 chemists who worked out what was going on with stratospheric ozone. But he saw this data before we published it as part of our work in the IGBP, International Geosphere Biosphere Program. And he said in the year 2000, we're not in the Holocene anymore. We are in the Anthropocene. So he was the first one to use the Anthropocene concept and word. Researchers before him had used other sorts of terms for human influence on the Earth system. But his was really direct and clean. Anthropo for human, scene as the next geological time period. And he said one thing really more specific, which challenged the geologists. He said, this is a new epoch in the geological time scale. So as an Earth system scientist, he was throwing the gauntlet out to say, hey, we're not in the Holocene, not just in common informal usage. We need to formalize this as part of the geological time scale. I'll get back to that in a moment. Well, one of the indicators, of course, on that graph of 12 is climate, and that's what a lot of people think about. So here is the contemporary instrumental record of global average surface temperature going from 1880 to 2017, last year. And you can see how remarkable the increase in temperature, again, since about the mid-20th century has been. We now stand at about 1.1 or 1.2 degrees above pre-industrial. Doesn't sound like a lot, but the difference in global average surface temperature between an ice age and a warm period is about 4 degrees. So this is very significant. It looks even more significant when we put it on a graph of what natural variability looks like. So this is the last part of the Holocene, the year 0 AD, Roman Empire time. And now we're going forward to where we are today. So there is natural variability in the climate. And you can see we can actually predict this envelope really well by looking at changes in Earth's orbital parameters. That's how we got those two blue lines. And it pretty much sticks within there. Medieval warm period, little ice age, and so on. An extremely small cooling trend over 2,000 years. This is in tenths of a degree now, not degrees. And then you see the human influence at the end, which is striking in its rate and its size. About 1.1, 1.2 degrees above the pre-industrial, which we usually take to be this period right here. Rates of change are enormous. When we look at the temperature and we look at that background rate of change over the last nearly half century, since 1970, temperature's been rising at 170 times the background rate. You don't see that back in the geological record until you see a catastrophic event, like the so-called PETM 56 million years ago, or when the meteorite struck 66 million years ago, and so on. So this is looking like one of those catastrophic events in Earth's geological past. CO2 increase over the past 2 decades, short time, but during that time it's about 100 times faster than when the Earth comes out of a glacial period. When that happens, CO2 rises naturally from about 180 ppm during a glacial to about 280 ppm during an interglacial. But it's rising 100 times faster now. Ocean acidification, the rate there, is faster than anything we've seen in the geological past for at least 300 million years. So we're seeing geologically significant rates of change, albeit over really short periods of time. So the question is, how much longer will these be sustained, and what are the implications if we do sustain them for very much longer? Everyone thinks about the climate, hugely important issue. What sort of gets slipped into the background is what I indicated on that graph of 12 parameters for the Earth system, 6 of which were the geosphere, many of them climate. The biosphere is really important. It's not just a passenger, it's an active player in how the Earth system actually operates. So we can look at what's been happening to the biosphere over the same time. This is one way of looking at it. A lot of people like to look at it this way. These are great extinction events. And when you have a great extinction event, it's normally considered to be greater than 75% extinction in a large group of families of organisms around the planet. We've had 5 of them before, symbolized here. But where we stand today in terms of threatened species, they aren't quite extinct yet, but they are threatened with extinction by the IUCN, we see very high percentages for most forms of life on the planet. Extinction rates are lower than this, but they're still much higher already than background rates. In fact, we can say that they are at least tens and probably hundreds of times faster than background rates. So the bottom line here is we are not yet at the Earth's 6th great extinction. We are headed that way. And given the trajectory we're on, within the next century or two, we will have completed a 6th great extinction event in Earth history. But I think an even more stunning statistic is this one. If we look at all the life on land, terrestrial life, that has a backbone, vertebrates. So that's us mammals and all the other mammals on the planet. It's birds, it's amphibians, and it's reptiles. And if we just combine all of our mass of our bodies, so if we take all of us humans, all of our weight together, 7.4 billion, we are 32% of the weight or mass of all of creatures on the land. If you add in our domesticates, our pigs, our chooks, our cattle, and so on, they comprise another 65%. So that means all wild creatures on Earth are less than 3% in terms of the total mass of life on the land. This gives you a really good picture of by how much humans dominate the biosphere today. So we talk a lot about the climate, and indeed it's an important issue, and we are changing the climate, but we are changing the biosphere even more dramatically as we change the climate. And so that's the really interesting puzzle for Earth system scientists, is we have to try to put this together and say what's happening to the state of the system as a whole. So the geologists have been challenged by Paul Crutzen, and they've gotten into the act by forming an Anthropocene working group. I'm one of the members of that, and much to their credit, in addition to a lot of geologists, they have people from other disciplines as well. And so they have a very clear definition for the Anthropocene, a really tightly formed question. Have humans changed the Earth system such that geological deposits, the stuff that are forming the strata, the rocks, forming now and in the recent past, do they include a fingerprint distinct from that of the Holocene? That's a really, really clear definition that we have to meet. And if so, when has the change become recognizable worldwide? Not just in one place, but synchronously worldwide. It's a tight, very strict set of criteria that we need to meet. Well, we've been going for about 7 or 8. I think we're just in our 9th year now. And we've done enough research, published enough papers, that we can start to address these questions. And so we did a survey of the 35 members of the Anthropocene Working Group. Our chair is Jan Zalasiewicz, who's from Leicester in the UK, a stratigrapher. And here's the conclusion. The signatures of human origin are well above Holocene norms and will leave a lasting signature. That's clear from looking at the strata that are already forming. The evidence is most consistent with a mid-20th century beginning. So it corresponds really well with the great acceleration graphs that we've produced. So in other words, those graphs which are looking at indicators above ground are already being reflected in the strata that are forming in ocean basins, in lakes, on the land, and so on. So now the last and next and important step is specific cores are being examined. You have to put together one main core with a bunch of supporting cores to get this formalized. These are some of the things we're looking at. You can see they're of human origin. Aluminium, concrete, plastics, synthetic fibers. You could add radionuclides from bomb tests and so on. But all of these are increasing from the mid-20th century, from 1950. And they're globally synchronous. So I think we have a wealth of data we can put forward to the geological community to say, this thing's real, it's definitely different from the Holocene, and we know when it started. The crunch time will come about 3 years from now when there's a big international meeting, and we will present the actual cores themselves for evaluation. Okay, but let's go back to the Earth system perspective and look more carefully at what the Anthropocene means. So here's our temperature graph for 2,000 years, the last 100 to 150 years. And these are the projections out to 2100 from the climate models. So we're sitting here about at this point. This is a low emissions, the lowest emission, which would get us to about 1.5 above pre-industrial. Here's the worst emission, high emission one. And there are a couple in between. So you can see that these look like fairly gentle curves anywhere from a degree. By the way, the 0 point here is not pre-industrial. It's a bit more recent than that. Up towards 4 degrees. And policy people who don't understand the Earth system say, well, that doesn't look too bad. Surely we should be able to adapt to that. All we need to do is put that in the Earth system perspective. So there's our graph. There's the spike going up here from the recent observed temperature rise. And here are the projections out to 2100. Now you can see what we're doing here. This is 1900, so this is a century from here to here. So 2100 is just there. So you see now that our Paris target of 1.5 to 2 in that range is already a really big change between what we are now, where we are now, and where we've been the last 7, 12, even 12,000 years. If I turn this upside down and say, let's cool this way, by the time you got to that point, you'd have the temperature of an ice age. So we're talking about geologically significant changes in the condition of the planet's climate. And we're talking about extremely short time frames. So when you look at this, we're pretty much committed to 2 degrees. We'd be really, really lucky to get 1.5, and it'd take a massive effort to do so. It'll take a pretty good effort to cap it at 2, but we still have a fighting chance at 2. But if we don't, and go to 4 or 5, a lot of people I talk to, not just in the natural scientists, but in the social sciences, say this is going to be a really tough world for humans to cope with. And we can't rule out the fact that contemporary society could collapse under that. So many changes in food supplies, water resources. Already we're starting to see migration, conflict, where climate change is playing a role. It would be much worse then. But the interesting thing from an Earth system science point of view is this intermediate zone here. Can we muddle through somewhere in between? And our view is increasingly no, because of tipping points in the Earth system. The Earth system behaves as a complex system. So it's not a linear system where the more you put in CO2 and other greenhouse gases from human activities, the warmer it gets in a nice, even pattern. So what are these tipping points, and how might they actually change the behavior of the Earth's system? So what we're arguing is if you go much above 2, you're going to go into the realm of these tipping points. They're going to take you to 4 or 5, even if you cut emissions to 0. This hasn't been proven yet. It's new research, but it's challenging the traditional view of many in the scientific community that climate is a deterministic system, even up to a forcing of 4 or 5. We're saying that actually may not be true. Here are some of the tipping elements we've done a lot of work on. There are 3 types. Melting of ice sheets at the poles, circulation changes in the atmosphere and the oceans, and changes in the large biomes around the planet, for example, the Amazon basin. So the question is, at what temperature range might these tip, and what are the implications if they tip? So if we look around, the Amazon already shows instability. We've lost, via 2 droughts and fires, about 10 years' worth of carbon storage. So this is going to shove more carbon in the atmosphere in addition to our emissions. The permafrost has an enormous amount of carbon that could be lost, 50 to 250 billion tons. The larger number is 25 years' worth of human emissions. This is a big number. This would blow the carbon budget just on its own. Right now, only very small emissions, but it's starting to melt, and we're starting to see it bubbling out. The question is there a tipping point beyond which it'll really take off? We're seeing ice change. The Arctic sea ice, year by year, more and more is being lost. We actually think we've crossed that tipping point. So in 20 years' time, you can sail up to the Arctic Ocean in summertime, right over the North Pole. Coral reefs, we may have crossed that tipping point. We may have crossed the point of no return. And given the momentum in the climate system, they may be basically an historic ecosystem. Ice is being lost increasingly from Greenland. This is the rate of mass loss of ice increasing. And worryingly, we thought Antarctica was stable. It's starting to lose ice as well. So this adds to sea level more than it directly affects the climate through albedo changes. Sea ice affects the reflectivity of the Earth, which actually warms too. All right, this is a geeky diagram, but this is what complex systems scientists do. And one of the things I have to say, first of all, is that the axes do not include time. So they include 2 things. They include temperature going up and sea level going up to the right. So basically what I'm doing here is taking this nice sawtooth pattern of ice ages, warm periods, and so on, and looking at it as a cycle. So here's a warm period, then the Earth slowly slides down into an ice age, spends a lot of time down here where it's cold, and then comes up here faster into a warm period. So our current warm period, the Holocene, is this bit here. So that would be here, and the previous cycles would be here, here, and here. So these top bits are here, the low bits, the ice ages, are down here, and that's the cycle in between. What we're saying now, though, is that this temperature spike tells us, and modeling tells us, we've broken out of this cycle already. We are not going into the next ice age, even if we got emissions to 0 tomorrow. We've already broken out of that cycle. And we've drawn this little ball as planet Earth today. It's sitting there, going away toward higher temperature and higher sea level. Now the question is, we don't know where it's going to go from there. Earth system science, complex system theory, says that right now it's humans pushing it up to about 1, and we say it'll probably be humans pushing it up to 2. But what we're saying is somewhere 2 or maybe a bit higher, these really kick in, these feedbacks, these tipping points. And they will start controlling the Earth's trajectory up toward what we call hothouse Earth. 4 or 5 degrees warmer, sea level could be up to 30 or 40 meters eventually higher. And we know these are stable conditions because we've seen the Earth in them in the recent past. This is the world where we actually meet the Sustainable Development Goals, where we cap temperature at 2 degrees, we become much better biosphere stewards, and we actually, humans, steer the Earth onto a trajectory somewhere between 1 and 2 degrees, and maybe eventually back toward Holocene-like conditions after several thousand years. So what we're saying is that there could be a fork in the road, a bifurcation point, that once you go down the hothouse, start on that, you actually then can't get back to a stabilized Earth. In other words, the Earth system is out of human control. Controversial theory, yes. But we know the Earth has behaved like this before. These are records from the geological past, 6,000 years ago. the mid-Holocene, 7,000, 260 ppm, 6 to 9/10 of a degree above pre-industrial. We've actually passed the mid-Holocene now. Temperature hasn't caught up already with our CO2, as we can see from the past. The Eemian, the last warm period, 125,000, 280 to 300 ppm, 1 to 1.5 warmer, similar, but 6 to 9 meters of sea level rise when it eventually equilibrated. Mid-Pliocene, this is an interesting one. 3 or 4 million years ago, this is where CO2 is, it's already in this range, heading for 450. That was 2 or 3 degrees warmer. That's consistent with the climate models. That's what they say is going to happen. Sea level rise was 10 to 22 meters higher when it got there. And then you can see an even warmer one. So we know the Earth can actually sit in these periods for thousands of years. Not unusual. Well, here are these tipping elements now showing their interactions in what are called tipping cascades. The idea is they tip at different temperature ranges, and we start tipping the ones at 1 to 3, which increase the temperature, which start tipping the 3 to 5, which start tipping the 5 and off. This is how a complex system actually crosses a threshold and the whole system moves to a new state. It's not simple, it's messy, it's a cascade, it's interactions, but once these start, they may be extremely hard or impossible to stop. How feasible is this? This is a new idea. It's not standard in the scientific community. Well, we point out to several things here. One is complex system behavior of the Earth system the last 1.2 million years. It's absolutely clear in the ice cores that the Earth behaves as a complex system with well-defined states and transitions between them. As I said just before in that chart, hothouse Earth conditions are accessible with the projected CO2 concentration we got. We could get there. Some feedback processes are the same that have operated in the recent past in glacial, interglacial transitions. We know them, we've mapped them, and we know how important they are. And observations show that some of these tipping elements are already vulnerable at 1 to 3 degrees temperature rise. Circumstantial evidence, yes. We're now developing more complex models that can actually try to simulate this to see just how feasible these feedback cascades are. So this is a risk, hasn't been much thought of, but when you look at the Earth as a system, this makes a lot of sense. All right, I've done my usual thing, which is to talk about the Earth as a natural system, biosphere, climate system, geosphere, and so on. But the really important thing now is there is a third sphere that is equally important, operating on the system and interacting with the system, and that is humans. So well, we're obviously changing a lot of things, but let's start looking at humans in terms of the Earth system as a systemic property, not as an outside force shoving stuff into the Earth system, which is what a lot of natural scientists actually do, and a lot of policy people actually think. Well, the first thing we did is we got clobbered really quickly when we published the Great Acceleration graphs by a couple of social scientists from Lund in Sweden. And they said, me, Paul Crutzen, other people, you got to stop talking about mankind or humankind as if it's one whole. Said it's not one consistent whole. It's a subset of humans that have actually caused the Anthropocene. It's the fossil fuel-driven, consumption-oriented, globalized economy. And that wasn't created by humanity in general. It was created by a subset of humanity, and that they are really responsible for the Anthropocene. So they're saying inequalities within the human species are really important. And they make a very good point. And we went back to the 12 Great Acceleration graphs, and they were dead right. That when you look at population growth and you look at economy, 18% of the human population drives 3/4 of the consumption. So they were right and made a very good point. So you look at this 18%, the wealthy part of the world, and say, well, is that the type of the world that everyone's going to, and is that something we should aspire to? And so a lot of social scientists were saying to us, wait a minute, the problem's in the wealthy part of the world. And one of the ones that is coming up really quickly, that's just an idea of some of the social problems that appear in the U.S. But one of the things that comes up is this inequality issue. This comes up time and again as something really fundamental about humans in the 21st century. My colleague Sandra van der Loo, who's a social scientist from the Netherlands, said, hey, you better look at this income inequality graph. It's really cool. So I did. So here we go, 1913 here, English-speaking countries, 1900 European countries. So what we're looking at is the top 1% wealthiest people. what percentage of the total income of a country do they commandeer? So here we see they're up 16, 18% in the early 1900s. And then you have the Great Depression, the stock market crash, World War II, somewhere in here. And then the Reconstruction after World War II was really egalitarian. So the English-speaking world was actually still increasing equality till about 1980. And then it switched really dramatically. There's been a dramatic increase in inequality in the English-speaking world. Contrast that with Europe and Japan, which followed the same trajectory to World War II, and then through their social and political systems have maintained a much higher level of equality in their countries. That's quite striking. When you look at the English-speaking countries, New Zealand's about in the same place. We're about the best of the English-speaking countries, much better than the US. But we're still going in the wrong direction compared to our European colleagues. Now, some social scientists, mainly economists, say, but this doesn't matter because wealth has increased so much that even the lower income people in these countries are so much better off that it doesn't matter that the wealthier is so much wealthier. Well, that was disputed by some really interesting work by two English epidemiologists, Kate Pickett and Richard Wilkinson. What they said was, no, it actually matters. And so what they did was they graphed against income inequality, where this is higher inequality. They graphed against that social problems that are typical of wealthy countries. You can see what they are. Teenage births, obesity, mental illness, addiction, and so on. The correlation was striking, really tight. They were heavily criticized when they published it in 2009. They updated it in 2015. The correlation is even stronger. The more inequality you have, the more social problems you have. And that seems to be a really, really robust outcome. Most of the English-speaking countries are in the upper right-hand side of this. Here's Australia. Here's New Zealand. The only English-speaking country doing better than us is Canada. The usual suspects are down here with low inequality and low social problems: Sweden, Norway, Finland, Japan. So there is an outcome in societies of inequality, no matter what the base wealth is. And you can start then to put this in the context of the Earth systems, that we're seeing some system incompatibilities here that are growing quite strongly. And we can see it in all three spheres. We can see it in the geosphere, where we have circulation patterns in the ocean and the atmosphere. And they are being disrupted, and they're being disrupted by growing circulation patterns of the human sphere. This is air traffic around the world. And you can see how rapidly it's growing and how ubiquitous it is. So we are putting trade, communication, transport, global patterns on top of the natural circulation patterns. And they are so large they are interfering with the natural circulation patterns. This is the biosphere, and this is what a lot of people think the biosphere still is, although we've shown before that these are less than 3% of the body mass of terrestrial vertebrates. But more than half of the biosphere now looks like this, required to grow food for 7.4 population of humans, and growing. And if we look at the human side of things, we still have close to 1 billion people who don't even have the basics of a decent life. And at the same time, we have an extremely rapid trend of urbanization with higher consumptive lifestyles, higher incomes, more wealth, and so on, and the growing inequality that we talked about. Well, there have been some commentators on this about how you start putting all this together. Clive Hamilton, whom many of you would know, an ethicist and philosopher here in Australia, has written a recent book, Defiant Earth, which he really starts unpicking the Anthropocene from a human point of view. Really well-written, challenging book. But as usual, Clive makes some strong statements. And he talks about the astonishing force of consumer culture that has swamped traditional customs, values, aspirations, replacing them with a devotion to money, materialism, and branded identities that has left tradition as smoking rubble. So in one sentence, he sort of encapsulates this incredibly powerful force that really is the underlying driver of the Anthropocene. This is a really interesting book, sometimes hard to read, but really very thoughtful. The systems view of life, looking at life from the first single cells that evolved here to Homo sapiens, and looking at the systems view of who we are, how we operate, but in particular the fact that we are not isolated individuals. We are incredibly social creatures, and that's why as you disrupt social systems, you start getting bad health outcomes. But they make a powerful statement too. Our world today is dominated by a global economic system with disastrous social as well as environmental impacts. Predatory capitalism. And this is really profound. We're the only species on Earth who destroys its own habitat, threatening countless other species with extinction in the process. Now, you could argue as an Earth system science that cyanobacteria did that. They led to the Great Oxidation Event, which basically destroyed their own habitat. But they didn't do it knowingly. We are doing it knowingly. We know exactly what we are doing. That's what Earth system science is saying. And yet we haven't been able to bend those curves yet. A lot of people have written about this. Thomas Piketty wrote a fantastic book, observation-based, not ideological-based, that capitalism as a system drives inequality and wealth. That is the way it is structured. So it's not really evil people. It is simply the way the system operates. Naomi Klein says the way it operates, it drives climate disruption simply by the way it's set up. Again, systemic property. And Jane Meyer says the same thing. When you get this extreme wealth, you corrupt political systems. It's probably more advanced in the US, but it's happening in other countries as well. So again, these are system-level properties. And the reason I put this up is because as an Earth system scientist, I think when people think about humans as a system, it all starts making more sense. So if we go on, what are some of the ways forward? I mean, it looks pretty dire at the moment. But in addition to all the problems, all the negative trends, there have been some phenomenally increasing attempts, and important attempts, to turn this thing around. This one is really exciting, the 17 Sustainable Development Goals that the UN has come up with. The most comprehensive set of goals that deal with human well-being and planetary well-being at the same time. The question is, how do we achieve it? So the Earth System Science community has tried to chip in with its bit by saying we have now enough science to say there are boundaries to how much you can change the Earth system before you destabilize it. And so we've developed planetary boundaries, 9 processes. We think we know approximately where the limits are and where we stand vis-a-vis the limits. And this, by the way, this framework informed the SDGs in terms of the global environmental targets that they have. And the idea of these planetary boundaries is to turn the trajectory of the Earth system away from this hothouse Earth and back down toward a more stabilized Earth. This is the planetary framework that we think we need to follow. Kate Raworth's a very, very clever economist from Oxford University. And she's done something that I think is really profound. She's saying, actually, we need to live within this donut. And the outer circle there, those are the 9 planetary boundaries. So we have to respect our planet. We have to have a stable planet for us to thrive. But we also need to look after human well-being in terms of equity issues, in terms of health, food, education, voice, all these sort of things. And she says we have to do it at the same time. Right now, we're dealing with some of these, not all, at the expense of the planetary system. And we've got to stop doing that. So she calls it donut economics. And she goes further and says, here's how you do it. First of all, you go away from simple cause-effect thinking to systems, dynamic complexity, in terms of the human system as well as the biophysical Earth system. These two are important. You design an economic system that, by the system attributes, it's distributive. It tends to equalize wealth rather than concentrate wealth, as our present system does. And second of all, it's regenerative by design. Right now, our economic system, by design, is exploitative. Just think of the word resources. Change that word to life, and you might get a different idea of what we should be doing. But she goes into much more detail and says you can actually build a system that humans can prosper in, but it's designed to deal with these other bad outcomes. So the problem is this. We really need to think about the biosphere, other life. We need to think about social welfare and, of course, prosperity. And we need to change from the view we have today, which is this view. This is the view that dominates most countries around the world, certainly Western countries and increasingly developing countries. Do we see change at the top? Well, you could get really depressed when you look around. There's Mr. Trump, President of the United States, age 71. Comes from a completely different era. Theresa May, taking her country out of the European Union. And increasingly, I think the Brits are thinking, I think we made a mistake, as more and more polls are saying. And of course, here in Australia, we have Malcolm Turnbull, age 63. Now, the interesting thing is we're just starting to see the new generation come on in some pretty important countries. There's Justin Trudeau in Canada, who has a completely different view of where Canada should go. And Emmanuel Macron in France, only age 39, has become the president of France, and more recently Jacinda Ardern in New Zealand, who's only 37, who has very different ideas of the way New Zealand should develop into the future. But the interesting thing about all these people is they don't talk much about climate change because they already get it. It is already a given for them. And that's a huge difference in the mindset. I'm going to close now with just a couple of overarching philosophical comments by colleagues of mine. One is Dipesh Chakrabarty, a philosopher, who really sort of sums it up very succinctly. We've built a human-centric system, political system, economic. It's about us. It's about becoming wealthier and so on. But he says most of humanity before this was actually life-centric. Interacted with the rest of life, was a steward for the rest of life, and that's what we need to do. My colleague Carl Folke up in Stockholm says it in 4 words. We need to reconnect to the biosphere. We're part of the biosphere. We evolved into the biosphere. We've separated ourselves from it. We need to reconnect from it, and reconnect to it. And that's the biggest challenge we face in the 21st century. But the last word actually should come from the oldest continuous culture on planet Earth, which is our own indigenous peoples here in Australia. And one of the elders recently passed away from the Noongar people, said very clearly what we ought to be doing. We're not here individually for a very long period of time, but we know what we should be doing, and that's to look after country. And that's what Indigenous Australians did for at least 60,000 years, probably longer. We're only a tool in the cycle of things. Notice they understood systems, cycle of things. It wasn't a linear type of thinking at all. We go into the world and help keep the balance of nature. It's a big cycle of living with the land and eventually going back to it. So that in a nutshell is a quick tour through the Anthropocene, where it came from and where we're going, and hopefully it gives us time to take pause and think about not only us as individuals in our daily lives, but the rest of the planet that we inhabit. So thanks very much. We'll have, I think, a very good discussion now. Thanks for your attention.
Thanks, Will. Very thought-provoking, I think. And without further ado, because I do want to get on to questions, I'll ask you to take a seat. I'm going to introduce our next 2 panellists, because I'm going to start. Exactly, it's interesting. You went from the old to the young, and I think that was my problem too. It's much better to have these young people to share their thoughts. So I'm going to introduce them. Belinda Wade, a lecturer in strategy in the UQ Business School, coordinating the corporate sustainability and business strategies for sustainability and innovation courses. And her research primarily examines organisational decarbonisation and sustainability, following from her doctoral research, which examined best practice carbon management within Australian businesses. So welcome, Belinda. And then Mohammed Arviandito, better known as Arvi, is a Master of Sustainable Energy student. He has 3 years' experience as a petrophysicist for a major Indonesian oil and gas services company. He graduated from the Institute of Technology Bandung in Indonesia and has a degree in geology. And he's currently interested in energy economics and the role of off-grid generation for rural electrification in Indonesia. So, I'm going to ask each of our young panellists a little thought provoker to see what they're thinking in response, and then I'm going to open up to you because I'm sure there's lots of questions that you've got for Will and obviously Belinda and Arvi. So Belinda, shall I start with you?
Sure.
So you've recently completed your PhD focusing on sustainability, and you've previously worked with energy businesses and modelling. So how do you see businesses today responding to the issues, and what do you think are the implications for the Anthropocene and going forward?
Okay, well, I think in my experience with businesses, and I also should mention I also run a sustainable business program, and I get the pleasure of taking visiting academics through a range of sustainable Australian businesses, is that when we look at climate change and the issues that are coming out of the Anthropocene, they're so broad. So we can either take the direct impacts in terms of climate change and extreme weather events and sea level rise, but also the indirect impacts. So if I break that into 2, I think I see in terms of the direct impacts, probably a less concrete and strategic focus within organisations. So we can see them do the future scenario planning. We see, in certain developments, like say at the airport, they'll factor those increased sea level rises into their planning. But I see, I guess, a devoid of strategy, so building it into the long-term strategy of the companies. And if we then go into looking at the indirect impacts, so if we're looking at sort of technological change and the impact of regulatory and legal aspects, we can see a lot of great examples, again, of things that are happening within organisations, say for, renewable energy and, treatment of water through reverse osmosis and minimisation of resource use. But again, I still feel that on the whole, we need a complete change in the way the cognitive framing, the dominant cognitive framing within these organisations to actually achieve, I guess, a more meaningful impact. So bringing on board those new business models which can lead to a reduction in our impact.
Okay. Arby, question for you, and then I might ask Will to respond, and then we'll open it up. So Arby, for you, as a Master of Sustainable Energy student, what do you think when you hear about Will deliver that discussion and his investigation into Anthropocene, and what are the implications or the questions for you when you think about your home country in Indonesia? Because I think that's one of those challenges.
I want to talk about the policy, climate policy in Indonesia. Actually, the government has acknowledged the challenge and the changes of climates, and it affects the vulnerable population in Indonesia. Our COP21 commitment is actually is a presidential decree. But the thing is, like, for example, in the energy sector, you also have the problem of equity and also the security of energy. That's why the government also inconsistently they put out the 35 gigawatt building program, and most of it is coal power plants. And that's the thing about the contradiction between the policy and what the commitment in this COP21 and the real problem in the society. And also that's an interesting point with the economic system in the 21st century. Like now we always think about an economic project. We value economic project based on the IRR, NPV, and it's like we discount the benefit in the future. So it's like it prioritizes consumption in the present day. So if we propose a new way of thinking, then we have to change the whole economic systems and the whole finance, how we evaluate a project, and I think that's a interesting thing to discuss in here. Yep. Did
you want to respond at all, Will, to that?
Yeah, just really quickly. I'll respond to Arby first, because I think what you're pointing out is a really good point and a very difficult problem. Is the development model that we followed in the OECD countries has easily become the dominant one around the world, and that's the one that a lot of developing countries are following, which is exactly as you described. And then I think what Belinda pointed to was the real challenge in changing that system, because quite often when I work with businesses of the corporate sector in consulting roles and so on, the common thing is to just think in terms of how do you modify the present system and deal with these problems, and then quickly people throw their hands up and say, we can't do this, it's all too big. Until you meet really disruptive people, disruptive in a good sense, technology people or people like Kate Rayworth who think outside the box and say, not only do we have to do this, we can do this. But it will be disruptive in terms of changing power structures and so on, and that's why it makes it so politically hard. I think it's the same thing that you might be seeing, Belinda, and some of the people you talk to, is that to get them to think to the really fundamental transitions we have to make, which are ethical and philosophical and so on, that underpin how we organize our economies. That's a really tough one. The only comment I'd say that's encouraging is when you look at this new generation of leaders and new generation of people, a lot of them don't immediately throw up their hands and say, impossible. They start thinking, well, how can we do this? Because they can start to see that their future is not so good if we keep going the way we're going.
Okay, so look, I'm going to open it up to the floor. We've sort of got about 10 to 15 minutes. I'm going to and then we've got lovely drinks and nibbles. I know some people are very hungry. But I was really interested, Will, when reflecting, and is that whole idea of we had the GFC, and I've always thought we sort of just stopped, took stock, and then kept going. And it didn't really create a huge amount of change in the way that our systems operate. You know, it was sort of a little bit of a blip, and then we moved on. And so that whole, I've always reflected on, you know, what did we learn underneath this capitalist society? I think it's quite interesting. So if you'd like to ask a question, please put up your hand. We've got Nicole and Estella with microphones. Can I please just ask that you introduce yourself and you keep your questions short? We don't need statements, a very quick question to any of the people on the panel. And we've got someone right here, Estella, so you can go first. But hands up if you like, because then, Nicole, can you maybe go up towards the back? Thank you.
Yeah, Gordon Buck from Arrow Energy. I was fortunate to hear Kate Rayworth during the week on the radio. I think she was on ABC Radio with that idea of the donut that she called.
Yeah.
One of the things that she talked about was that trickle-down economics has a lot to do with inequality that we see in society today. And she said that it was based on flawed research. I was just wondering if you had a comment on that.
Estella, do you want to grab the mic? Thanks. Will?
So your question was about the research on trickle-down?
Trickle-down.
Economics.
So she said that the idea of trickle-down economics was based on some research that